We're going to listen to Reinhard Genzel talk about the amazing story behind the study of the compact object in the galactic center, a 40-year journey. Reinhard Genzel earned his PhD in physics and astronomy from the University of Bonn in 1978. He held a postdoctoral position at the Harvard-Smithsonian Center of Astrophysics, followed by a Miller Fellowship at the University of California in Berkeley, where he became full professor in 1985. In 1986, he was appointed director of the Max Planck Institute for Extraterrestrial Physics in Garching. Reinhard Genzel has been spearheading the high spatial resolution imaging and spectroscopy studies of the motions of stars surrounding the Sagittarius A radio source in the Milky Way center using the European Southern Observatory facilities in Chile. As we are about to hear a fascinating and still evolving story. Professor Genzel, the floor is yours.
Ladies and gentlemen, dear colleagues, it's a great honor and a pleasure to be here and speak to you about the research we have done in trying to establish that in the center of our nearest galaxy, the Milky Way, is an object which is a massive black hole of 4 million solar masses beyond any reasonable doubt. I've called this the 40-year journey. It's been a long time. Many people were involved. Experimental work has been ongoing for these decades to improve the sensitivity, the accuracy of positional measurements, and the precision of data to come where we are now and where we can say with some certainty what I will tell you. Many people have been involved in my own group, people before me, mentors, but also many students and postdocs. I'm very, very glad to have been able to work with such a great crowd of people. And I also would like to emphasize the great work of our team in California who have been competing with us. But in the end, of course, we have come up with the same basic result, which only strengthens the overall believability of the result. Now, over these decades, of course, there were several phases. So I'll give you this talk in 5 phases. First, the motivation, and then 4 phases within the program which I participated in. Now, let's look at the backdrop. Of course, we know that the theory of general relativity is 100 years old. And the mathematical refinements went on for a number of decades, ending in the 60s with the so-called Kerr space-time metric and the work of Penrose on the ergosphere and others. Roger Penrose being the one who is being honored with the prize this year as well. So this theoretical foundation gave us the idea, the perspective, that there are objects which one would call black holes, which basically are not communicating from the insides with the outside, but can have tremendous impact on the gravitational field, the space-time surrounding it, and therefore influence their environment. Now, this was all theory until the 60s, when several things happened. X-ray astronomers started observing very intensely X-ray emitting binary stars, some of which we now believe are stellar black holes. And that's the most important thing for this talk, the quasars were discovered. Initially by radio astronomers, and then optical astronomers discovered that these objects in optical images look like stars. Yet in their spectra, there's evidence that spectral lines, which are in the laboratory very well known, are shifted by such an amount as to make these objects very distant, many hundreds of millions of light years away, such that what looks like a fairly faint star really must be a tremendously luminous object. This one, the first one, has 1,000 times the luminosity of our entire Milky Way, all coming from the central light year or so. Theorists thinking about this then found out that it was basically impossible to explain the radiation produced in these quasars by normal fusion, like in stars. But, and that's the surprising thing, when material spirals into a massive black hole, before the material disappears in the event horizon and therefore is, escapes from our line of from our view, it can release enormous amount of energy due to the gravitational energy lost, and that can be up to 40% mc squared. So, surprisingly, paradoxically, therefore, the model of massive black hole paradigms for the explanation of quasars was invented. But of course, how would you prove that? Prove that in the sense that you cannot only observe phenomena like high energy radiation or these spectacular radio jets of relativistic plasma emanating from many of the quasars. This is indirect evidence for a very energetic object, but not proof in the sense of actually showing that there's a gravitational potential as compact as you would have to have for a massive black hole. So how would you prove that? In a very famous paper in 1971, Linden, Bell, and Rees then proposed that whilst it's impossible to measure effects of gravity in distant quasars, if all galaxies would have central massive black holes, just most of them not very active in terms of accretion, well, then you could use nearby galaxies, in particular also the center of our Milky Way. So that's how our Milky Way center became center stage and evolved from there to a laboratory. So let's take a trip from the outer parts of the Milky Way into our disk galaxy towards the center. Now you see immediately in optical light there are these dark patches. That means that there's a lot of dust between the stars, which actually prevents us from seeing into the center of the Milky Way. So to see there, we have to switch to longer wavelengths, infrared, radio, or shorter wavelength, X-rays. This is an infrared image, which we can now make with modern telescopes, which shows us the innermost region of our Milky Way being a very dense star cluster. This is shown here in the blue region. And in the center of this star cluster, as you will see in a second, radio astronomers found very intense radio emission, in particular a very compact radio source. Surrounding that radio emission, in green here, is gas, very dense neutral gas, as well as ionized gas, the so-called mini-spiral in ionized gas. In fact, that was the first path towards looking whether there is a central mass. Basically, what one does is to look whether this gas is orbiting and look from the velocities what the mass would be. So indeed, a group around Charles Towns at the University of California with his students started looking at this ionized gas streamers here. You here see how the velocities change along this streamer here, and the numbers here give you the mass which would be required if this would be a free-falling, if you like, parabolic or elliptical orbit, and the numbers are 2, 3, 4, 5 millions of solar masses. So that was the first evidence that there was a lot of mass there, more mass than the stars would allow. Then the next stage was the radio source. Many years have been used to refine the measurement on the radio source. On this diagram, where you here have wavelength versus size of the source, you can see the shorter wavelength you go to, the smaller the source becomes. And spectacularly, when you go to the millimeter waves, here's 1 millimeter. The size of the source is 10 micro arc seconds. To give you a feeling, that's about the size of a euro coin on the moon. That's how compact the radio emission is. And in fact, that would be the event horizon size of a 4 million solar mass black hole. So the combination of this mass being large and this size being small was the first evidence in the 1980s that there might be something in the center of our Milky Way. So here on the left side, one could take the various measurements here and see that this mass was between 1 and 4 million solar masses. Not very accurately initially, maybe 50% or so. On the right side, you see, as a function of distance from the center, the mass, and here you see that within about a parsec or so, there seems to be a constant mass. That's an indication for a concentrated central mass, but still at a very large number of event horizon radii, 1 million. But it was the first evidence. How to go from there? Well, you want to go further in, and you want to use indications which are more stable and more easy to interpret than gas, which can be pushed around by forces other than gravity. And these are stars. And so in the 90s, two groups, one in Europe using telescopes in Chile, and one group in California using the Keck telescope, starting using the new developed infrared imaging detectors for the Space Telescope to build cameras which allowed very short exposures. The trick is that when you take a picture in the optical or in the infrared, then of course the Earth's atmosphere will blur the image such that you cannot make a very high precision measurement. To measure the motions of stars in the sky, you want to have very accurate positional measurements over time and see whether they change. So this was the first technique both groups used, the speckle techniques, as you see here. You make short exposures and freeze the motions of the Earth's atmosphere, and then in post-processing, you basically add the images to get about a 5 times improvement in the angular sharpness of the images over what you can do with normal detection. The second technique which had to be developed is to get spectra, because the motions on the sky give you two motions, and the Doppler motions along the line of sight, which is the third, you can get through the spectra from lines in the stellar spectra. For that, we developed what is now called the integral field unit. Basically, a normal spectrometer just disperses the light in one direction and doesn't allow you to image. But by using an image slicer, you can basically generate a huge long slit which decodes the 2 dimensions, and then you bring this through a spectrograph which disperses the light. And then in the end, in the computer, you can put that back together. So using these techniques, a few years later, we had sharp images of the central light years, and we could look for changes on the sky of their positions. Here's an example. The green cross is the position of Sagittarius A star, that radio source, which is so compact. This is one light month, this circle, and you can see from time to time to time, from one year to the next, in 3 different colors, the position of this star, very near Sagittarius A star, clearly changes. If you look up, then that's a motion of in excess of 1,000 kilometers per second, something which you see not in the solar system. So these stars are whizzing around at a speed of more than 100 times the Earth around the sun. So that's already a qualitative indication of a strong mass. And is it a point mass? Well, okay, Kepler's laws tell you that if you have a central mass and objects are moving around it, and the further away you are, the slower. And indeed, when you look here, the innermost stars move obviously very fast, while the other ones here, do not show this prism effect. So that's Kepler's laws in color, so to speak. And indeed, when you make this more quantitatively, you can derive then the mean speed of the stars as a function of distance from the radio source. That's what this is. And this tail here is indeed the first quantitative indication that indeed there is a 4 million solar mass or 3 million solar mass object in the center, and further out when this flattens, that is the effect of the star cluster surrounding it. So that was the second phase. That was until 98, with stellar motions making more precise estimates of the stellar mass. Now you see we are, at the level of about a little over 10%, and a factor of 5 or so inwards. So it's both a more precise measurement of the mass, as well as concentrating that mass on a smaller region. So by that time, it was already fairly difficult to construct reasonable alternatives. So the path was, this could be a black hole, but now we have to exclude alternative options of other configurations by going closer and closer and measuring more and more precisely. Well, how could you go from this phase onward? Well, here we are measuring basically the average of the motions. Now we would like to see actually orbital motion, direct orbital motion of individual stars. That's much more precise. But mostly in astronomy, these kinds of motions can only be detected over many hundreds of years. That's why nature came in and helped us and gave us some stars which were not supposed to be there, namely very, very close on solar system scales. And those indeed move fast enough that we can see motions. So by the early 2000s, both groups were working on 8-meter glass telescopes, the biggest telescopes we have now. And we had both equipped these telescopes with what is called adaptive optics. So instead of the speckle imaging, we are now correcting the wavefront before we detect it and make sharp imagery right away. That gives us a lot of sensitivity and high precision imaging. By 2000, Andreas' group saw the first deviations from straight motion, accelerations. So that gave us already hope that maybe we could see these accelerations for a number of stars. In particular, this one here had one of the possible solutions. You see there are 3 possible solutions, which was an orbit of only about 20 years or so. And indeed, 2 years later, both groups saw that this star, whose orbit you now see, highly elliptical orbit, approached the galactic center to about 17 light hours. Moved there at about 7,600 kilometers per second, tremendously fast, and on a distance scales of about 3 times Neptune's orbital radius. So if you put this into Kepler's laws, that gives you, again, 4 million solar masses. The same 4 million solar masses we had before, but now concentrated on the scale of only 17 light hours. Now, this is only one of the stars we followed. As you see in the movie down below, in fact, we have partial orbits for about 30, 40 stars. Yet this is the best one. So at the end of this stage, which is a few years ago, we had ever more precise measurements of the mass. And what's more important, because of this close approach, we could exclude that the mass is any more extended than about 100 times the event horizon size. So by now, by that stage, the exclusion principle was very powerful. You could exclude all kinds of hypothetical situations, including what one would call dark astrophysical clusters, like, for instance, a conglomerate of neutron stars, 1 million neutron stars, or stellar black holes or something like this. So there's very, very little lift. 4 million solar mass black hole, and perhaps this thing here, a so-called boson star. So here we are. We have already very good evidence. Do we stop? Are we finished? No, we are not. Now we are looking at this as a laboratory. Not anymore to say, is there a compact mass? We are certain of that now. But now we want to know, A, is it really a black hole in the sense of general relativity? And is general relativity the proper theory? Also in these extreme environments which have not been tested. For that, we have to still make better measurements. So by 2004, we talked to ESO, the European Southern Observatory, and proposed to build a new instrument. A new instrument which would allow us to combine the light of all 4 8-meter telescopes into a so-called interferometric telescope, very well known from radio techniques, of over 100-meter diameter. So a 100 over 8 meters is a factor greater than 10. So actually it's more than an order of magnitude improvement in resolution. So we built this instrument we call gravity, which brings the light together from all the 4-meter telescopes. It's underneath here. You have to make all kinds of corrections, etc., which are all in tunnels underneath this device, and has been built by the European Southern Observatory, while we built this new instrument which had 3 milliarc-second resolution and a astrometric precision coming close to the event horizon scale. The star, in the meantime, was doing its orbital period and was coming back. And we were ready. So that in 2018, when the next peri occurred, we could use the interferometer now to use this high-precision tool to really look very, very closely. By the way, you can see that here you see the star in the very close to peri, and you see the black hole itself. I'll come back to this later. So the experiment, in fact, is now actually conceptually very simple. You measure directly on the sky the separation between what you think is the center of mass and the object. Here, near peri, we could see the motion every day. Previously, we had to wait for a month or two. And we had a very precise definition of the orbital parameters of this ellipse, and thereby a high precision on the mass. And now we can begin to look for effects of general relativity. And in fact, the first one is the fact that when light from the star comes to us, when it's very close to the massive black hole, it has to climb out of this potential well, which is basically leads to a redshift, to a loss of energy. And here, relative to a Newton orbit, is in fact this redshift, which we have measured, in comparison to what you would predict from general relativity, which is the blue scale. So that was already the first triumph and the first evidence that indeed GR holds, very important. This was, confirmed by the UCLA group 1 year later, and the first step. The next one is to actually show that the equivalence principle holds, and in particular, in this particular form, the positional invariance. And that we can do because in the spectra of the stars we have different atoms. Here is helium, and here's hydrogen, and here's helium. So we have different atomic clocks. And according to Einstein's theory, the results should not depend on anything but the gravitation shouldn't come in, that there are different atomic clocks. And indeed, the results we get from the different tracers agree to within a few percent. The next effect expected is the fact that while in Newton's theory, a planet orbiting the sun on an orbit would hold its position in the plane if there's no other object nearby. But in general relativity, that's not the case. There is a precession of the orbit, which depends on the distance the star comes to the object and the mass. And so for the star S2, relative to a Newton orbit, and setting an angle equals to 0 up here at Apo, near Peri, this precession is maximum. You see basically in x-coordinate here is a kink. Or in angle, it's a change by about 11, 12 arc minutes per orbital period. So that's the prediction, and that's what we saw with gravity. Okay, here are the different measurements in x. So you see clearly this kink, and here you can see the change in angle, and indeed exactly as predicted by general relativity. So that's very, very important, because it shows us that indeed GR holds also in these extreme environments which have not yet been tested. Now, how close can we come to the center? Would it be possible to actually probe the region right around the event horizon? Well, actually, in the early 2000s, the X-ray astronomers and then we discovered variable emission in the infrared and at X-rays from the black hole itself. Continuously variable emission. And the theorists, in particular Broderick and Loeb, had proposed that what you see here are accelerated, energized electrons, which basically are formed in this hot plasma right around the black hole as the gas is orbiting, thereby forming hot spots for few tens of minutes. If so, you might be able to see the motions of these hot spots. So indeed, in 2018, on 3 occasions, the black hole got brighter than its normal state by about a factor of 100 or so. And we could see, indeed, these motions on the scale of, about 5 times the event horizon size, or 6 to 10 times the gravitational radius, with orbital periods of 40 to 50 minutes inferred from this. This means the velocities are speed of light, which is exactly what you would expect if these hotspots would move in Keplerian motion, if you like. Another thing here is that this emission is polarized. So that tells us that magnetic fields are present, and from the properties of the change of the direction of the magnetic field with time, which we can infer from these data, we find that the B fields is likely poloidal, so along the axis of the black hole and not in the orbital axis of the motion. That's surprising and probably indicates that the galactic center has a very, very strong magnetic field. This will be very important for the future to research further in order to understand this strange but highly exciting environment around the black hole. So here we are, after phase 4, Peri has happened. Now, as you see, with gravity in particular, our accuracy of measuring the mass is better than 1%. In fact, the statistical uncertainty is 0.3%. So that's a precision measurement, something which you can do not very often in astronomy. And we can penetrate now basically from the sphere of influence, where we showed the first measurements in phase 1, all the way inwards by 6 orders of magnitude close to the event horizon size. Are we done? Well, it's very likely that this object we are looking at indeed is a black hole. We don't know its spin yet, and we would have to know that in order to begin to understand whether the Kerr metric holds. And then we would have to test whether the quadrupole moment of this object fulfills what we call the O'Hare theorem. If we know that, then we would in fact have the final result that GR is indeed correct at the scale of the event horizon, which is the closest we can come. That we do not have yet, but that's where we want to go. So after these 40 years, I would say, the Galactic Center has been extremely helpful to astronomy and to physics. 2 groups have used this to push ever further, and many questions remain or go beyond what we have now but we now have evidence indeed that these objects, which were theoretically discussed by Roger Penrose and others, actually are realized in nature. Thank you very much.